everyone. So my name is Wang. So I'm from Imperial College London. I will talk my work. That's the last work of my PhD. It's called Rotogate. So human work. Yeah, human works in different kind of ways. They have a lot of creativity. Work like this, like this guy. But what's the fastest and most efficient way? Maybe they're working like a whale, maybe the most one. How to do that? Just add a whale. Simple. But the thing is, we don't want to add whale on the human arm. Wear shoes, more actuation, more joints. So what's the other way of doing this? So this comes out of the idea of the Rotogate. Exactly. So actually, this comes from inspiration from the Interstellar. So you get a very cool robot, and this kind of rotating gate, it looks very smooth, very fast, not very efficient. They work like whale. They can also work normally, right? So let's combine by itself both work. So actually, the idea of this kind of Rotogate is very simple. So you work from the normal gate, and then normal gate is kind of like rimless wheel, but it's only like you cannot switch. And instead of this, you do some kind of active rimless wheel, right? You just rotate your leg around and do this. But the question is it possible there is a robot that can realize this kind of gate? Seems almost impossible. So we build a robot that might make this possible. So this is a style robot that I built at my life. So it's a straight like knee-lace like the walking robot. So it has each leg. It has like 5 joints. It has prismatic hip slide joints. It has hip hitch and hip roll. It also has 2 ankle joints, so we can do street walking. And it's also very low cost because most of parts is 3D printed. This is an old design. We have some cycloidal gearbox, but later we replaced with T-motor. It still works because the leg is very lightweight. In total, each leg has like 3.5 kilo. It's very lightweight, so it's possible. In total, it costs around $6,000. It's not expensive at all, so it's very simple. I also show the video. So this is the video that we did in Mujoko and trained with reinforcement learning. So it's walking blindly. But working quite nicely, you see. And we can, really transfer this IR policy on the real robot, 0 shot. No problem, and you can resist a minor pushes. So we are, at first we are really afraid it might, okay, sorry. Okay, I don't do speed up, sorry. So I will come back to the Rotogate. So the idea of Rotogate is basically simplify the problem into optimize only the swing leg trajectory. We assume like the center mass moves like linear vertical pendulum, and then we model the leg as a single rigid body and do trajectory optimization. We just put path constraint, the state, and start and end state, and no penetration, kinematic limit, and motor limit. Because we know we know the motor, so we put also kinematic and electrical energy. So this is the result. So this is the result shown in 3D. Looks very nice. And also we can also do this for the same thing for the normal walking gait, right? The only difference is the leg, they touch ground at different ends. And this is the minimum maximum length. We also do some very simple study. So you see we fix the step length 0.6 meter, and then we increase the speed. I want to say at which time, which point, the rotor gate outperforms. So it's around 1.1 meter per second. We also do something like, we fix the speed and then we increase step length. And at this part, rotor gate doesn't outperform because it had to keep its leg in the air for some time because much. And we also put this on the simulation. It's very simple simulation. We get some issues with whole body controller because it's become crazy when the leg rotates on the other side. So we just do a simple feed forward, torque plus feedback, PID transition, and this work like this. Okay, so if you get more questions, you can also come to the poster. I will have a posting session tonight. Thank you.
So, a couple things. So this is cool. I love these cool alternate morphologies. Does it look like there's any impact when that thing's hitting the ground? The legs are hitting the ground.
So this is the big issue that we have. So we didn't try to optimize the impact. Actually, we put the start and end state as a zero velocity of the leg. So it's kind of like minimize the impact. But the problem is sometimes if the track is not good, it will slip. So it's a problem.
Yeah, I mean, which kind of goes to the other point I was looking at. I'm like, far be it for me to argue with the scientific stylings of Christopher Nolan, but like you said, that thing was smooth. And last thing I think of a ringless wheel is smooth. Are you confident that a ringless wheel can become smooth with effective control?
Yeah, maybe.
Cool.
Yeah.
Okay, so I'm wondering, you started with the idea of becoming more efficient, more economical, if you will, right?
Yeah.
And this is still, I'm thinking of the contrast of this and versus like a compass gate walker, which swings under gravity to reposition the leg, whereas this one takes power.
Yeah.
That seems less efficient rather than more, and so I'm wondering, what's the sequence of principles that you're using to lead this toward being highly economical?
Do you mean the energy economically?
Yeah.
So I don't really think that much. I think this idea is very interesting, very cool, and just work on that. So I do this optimization, just trying to minimize the energy cost, and then do a brief search, and then I get all this data plot and say, okay, at this point, this will be more economical. I don't do any analytical analysis about this kind of thing.
So is that optimizing the behavior of the design or the design itself relative to others?
Optimizing the mechanical cost, the cost of transport of the swim leg, basically.
By way of a controller, not a design, right?
Yeah, right, okay.
You computed the speed when it's more efficient, right?
Yeah.
It's something like 1.1 meter per second.
Yeah.
Like, do you also consider somehow like the dimensionless velocity, like to make this dimensionless? Because it somehow now depends on the link length and.
Oh yes, yes. Unfortunately, I didn't do that. Yeah. Because this is a model that I get for the real world products, and also we put the base at the middle of the link, like this. Sorry, yeah.
How does the road not fall in the simulation?
We fix the height. Yeah. Otherwise, sometimes it's really easy to fall down.